In our last installment, I told you that I would show you that to prove to you that the direction of the acceleration and the force causing that acceleration is toward the center, it is centripetal. To start out doing that, we want to take a look at how we treat vectors, both addition and subtraction of vectors. So when we add vectors, we could say the vector a plus v equals the resultant vector. So we have a plus b gives us this resultant. Subtraction of vectors is really addition of a negative number. So in that sense, there's really no such thing as subtraction. There's only adding a negative number. So we could write that as a plus the opposite of b, negative b, which is in the opposite direction, to b. So if we were to have a plus b like this, minus b is a vector equal in magnitude, equal in length, but in the exact opposite direction. So this represents minus b. So a plus a negative b is this resultant, and we can see they yield very different things. And this is how we do it graphically to determine the difference between two vectors. So if we have constant speed in a circle, like mentioned in the previous installment, there's a name for that, and we call it uniform circular motion. The uniform means the linear speed is uniform. Uniform meaning one takes one form. It also means that the centripetal acceleration is uniform. If the centripetal acceleration is v squared over r, and the v is constant, and it's on a circle, r will be constant, and the speed will be constant, so the centripetal acceleration will be constant. And so that's what we mean when we have uniform circular motion. So if it is traveling at constant speed on a circle, is that object accelerating? And that's hard for us because our intuition tells us, well, since acceleration is the rate of change in velocity, if the velocity isn't changing, then the acceleration must be zero. If delta v is zero, then the acceleration must be zero. But we have to remember that velocity is a vector. And vector quantities have two elements to them. They have their magnitude and they have a direction. So if the speed, the magnitude alone of the velocity is the speed, we could have a change in velocity if there is a change in direction. So delta v occurs when there is a change in direction. And this is a very hard thing for us to get our minds around. It's a difficult thing for us. How could something be traveling at constant speed? So the irony in that is that when we are in our car traveling down the highway on the Earth is actually curved, and even if we have our cruise control set at 55 miles per hour, we are actually truly accelerating. We're experiencing centripetal acceleration. But also that change in direction is so small that it means that acceleration is so small. And so, as the change in velocity goes to zero, the acceleration goes to zero. And it's hard to quantify the direction in this case, but we can see then when we are on the Earth, since it's so close to a straight line, the change in direction is very, very small. So therefore, the acceleration is very, very small and actually not even detectable in our interaction with it.